So in this video, we're going to look at using the disk method for finding the volume of revolution when the axis of revolution isn't one of the coordinate axes. So in the examples that we've done previously, we've either revolved around the x-axis or we have revolved around the y-axis. But it isn't necessarily the case that we need to revolve around the x or the y-axes. So in this example, it says find the volume of the solid generated when the region bounded by f of x equals 3 minus x squared and g of x equals 1 is revolved around the line g of x equals 1. So we have a parabola opening downwards, and we have g of x equals 1, and we want to find the volume of the solid that we get when we take the region bounded by those two functions and revolve it around the line g of x equals 1 or y equals 1. So we're revolving around the line y equals 1 instead of around the x-axis. The idea here is that the principles at play, though, are the same as they were when we revolved around a coordinate axis. So the bounded region, this is the region we want to revolve around the line y equal 1, is shown here below. So I cut off the parts of the parabola that I don't need, and I want to focus on the bounded region that I want to revolve around the line y equals 1. And if I'm going to revolve around the line y equals 1, I'm going to draw the characteristic rectangle of revolution with respect to the line y equal 1. And then I'm going to look at this and say, hey, when I revolve this, it's going to create disk or cylinders. How would I calculate the volume of one of those disks or cylinders? And what I want to recognize is that right here I'm still going to have dx slices with respect to the x-axis. These widths are going to be delta x's, and the radius of my characteristic rectangle is going to be this distance between the upper function and the lower function. So this will be my radius, and I need to, because I have dx slices, I need to describe my radius as a function of x. And then what I want to recognize is that the radius with respect to the line y equals 1 is just going to be the distance between the upper function and the lower function. My upper function is f of x. My lower function is g of x. So the radius of revolution, which is just the distance from the line of revolution to the upper function, is just going to be given by f of x minus g of x. So if I think about calculating the volume that I get when I rotate with respect to the line y equals 1, I'm still going to have cylinders. So the volume of a cylinder still is just pi r squared h. So if I start to set up my integral, so the volume I'm interested in is going to be pi times the integral of r squared, but r needs to be a function of x, so it's going to be r squared as a function of x because my heights are dx's. So this is just the volume of a cylinder, pi r squared h is just dx. So the pieces that I need to finish this off, I need to understand what do my limits of integration need to be, and how do I describe my radius, the heights of this rectangle of revolution, this characteristic revolution, as functions of x. So I have two choices here. I can either integrate from this intersection to this intersection, or I can use the fact that I have even symmetry with respect to the y-axis to ignore that half of the bounding parabola and just integrate starting right here at 0 to what is the x-coordinate of intersection there, but then we would need to double the volume. So my choice on this would be to double the volume of the volume of revolution I get when I go from 0 to whatever this x-coordinate is, because it's always nice to have 0 as a lower bound of integration. So I right away need to know this intersection point so I can establish my upper bound of integration. That needs to be done. And what I want to recognize is that to find the intersection here, I just need to set f of x equal to g of x to determine where they intersect. So f of x is just 3 minus x squared, and g of x is just equal to 1. So subtract 3 from both sides, multiply both sides by -1, take the square root of both sides, and I get plus or minus the square root of 2. So right here, the x-coordinate of this intersection is the square root of 2. So my upper bound of integration is the square root of 2. This intersection, the x-coordinate there, is negative square root of 2. So if I didn't double it and use even symmetry, I would be integrating from negative square root of 2 to 2. But it is going to be much easier to use symmetry and throw away that half of the graph and double the result of integrating from 0 to the square root of 2. So here's my characteristic rectangle. The radius is the difference between the upper function and the lower function, or f of x minus g of x. So my radius is just going to equal my upper function minus my lower function, which will just equal the 3 minus x squared, minus the lower function is g of x equals 1. So we wind up just getting 2 minus x squared. So I'm going to update my volume calculation. It's going to be 2 pi from 0 to the square root of 2. It's going to be the square of the radius, but my radii are given by 2 minus x squared, and my rectangle widths are dx's. And then to integrate this, it's probably going to be easier if I multiply this out first, or expand this expression. So I'm going to get, when I do 2 minus x squared I'm going to get 4 minus 2 times x squared twice is minus 4x squared. Minus x squared times minus x squared is going to be plus x to the 4th power dx. And now it's just a matter of integrating. So I'm going to get equals 2 times pi times, integrate 4, I get 4x, minus x squared is going to become an x cubed, so I need a 4/3 x cubed, plus x to the 4th will become x to the 5th, so I'm going to need a 1/5 x to the 5th, and I'm integrating from 0 to the square root of 2. Now I want to notice that when I plug in my lower bounds of integration, it will kill these inside terms because I'll get a sequence of multiplications by 0, so I don't need to worry about my lower bound of integration. So I'm just going to go ahead and plug in my upper bound of integration. So I'm going to get 2 pi times 4 times the square root of 2 minus 4/3 times the square root of 2 cubed plus 1/5 times the square root of 2 to the 5th power. And then I can do some simplifying. I have 2 pi, I have 4 square root of 2, and I want to recognize that if I take the square root of 2 and I cube it, for every pair I get a 2, so this is really going to be equal to 2 times the square root of 2. In other words, think about this as being 2 to the 3/2 power, which is 2 to the 1 1/2 power. So we get 1, 2 coming out, but we still have a 2 under the square root. So root 2 cubed is 2 root 2, so I'm going to wind up with 4 times 2 is 8. So I'm going to have minus 8/3 square root of 2 from simplifying this, plus, and here root 2 to the 5th is really going to, I'm going to get 2 2's out of this. For every 2 I get a 2, so I'm going to get 4 square root of 2, or in other words, this is really 2 to the 5 halves, putting it in rational exponent form, which is 2 to the 2 goes into 5 twice, and I get 2.5 as a mixed number, so I get 2 squared is 4, and I get the square root of 2 left over. So I'm going to get 4 times 1 is 4/5 square root of 2 coming out of there. And then to combine these inner terms, I need a common denominator, and it looks like 15 would work. So I'm going to get equals 2 pi times, I get a common denominator of 15. So this is going to be multiplied by 15 over 15. So I'm going to get a 60 square root of 2 from this term. This will need to be multiplied by 5 over 5. So I'm going to get 40 minus 40 square root of 2 there. And this would be multiplied by 3 over 3. So I'm going to get 12 plus 12 square root of 2. And then I can simplify. So I'm going to get equals, it's going to be 2 pi over 15 times, so I'm bringing the 15 out here. I'm going to get 60 minus 40 is 20, plus 12 is 32, square root of 2, which final simplification, I get 32 times 2 is 64 square root of 2 pi all over 15 as the volume of I get when I revolve the bounded region about the line y equal 1.